All right, let's get started. So yesterday we were working on another one of these bridge circuits. We were going through and we're solving for all of the voltages. And like I was telling you guys yesterday, if we solve or we Thevenize this guy across R3, that's going to make it so that we have to use simultaneous equations and possibly Thevenize on a second resistor as well to solve for all the voltages. If we choose one of the other four resistors to Thevenize, we can then go back through and solve for the entire circuit. So yesterday, we ran through. The voltage we were looking for was from A to B, and so we had to come through and we had to solve what the voltage drop across R2 was and across R3, and we ended up with a Thevenin voltage of 60.756 volts, and that's where we left off. So now, what we got to do is we need to determine the resistance for our Thevenin circuit. Now again, the steps for finding Thevenin is we short the supply and we solve what the resistance is going to be looking from points A and B. Okay? So, we'll just kind of slide this over and we'll do this on the side so we can see everything. So this is, we're just moving this line in a little bit so to make it easier to fit it all on the one screen. So what we want to do is we want to find out what's in series, what's in parallel. So we're going to start with point A. And what, excuse me, and what is point A connected to? A is connected to R2, R5, and R4. So we'll draw in those connections. So we got R1, or sorry, R1 is the one we took out. So R2, R5, and R4. Now, we're going to look at what all these other guys are connected to. So what is R2 connected to? R3 and R4. So we know we're going to have a connection here, right? Because that's the only thing R3 is connected to is R2 and R4, so we can make that connection there. And there's only one connection between the two of them. We good there? Okay, what about R5? What is the other side of R5 connected to? R3 and point B. So the rest of R5 is going to come down, connect into R3 and point B. So now we can find the resistance across the circuit pretty easily. What's in series? What's in parallel? R2 and R4 are in parallel. And then what? They're in series with R3. Questions about how we got there? You look confused, Zach. We redrew the circuit to solve for voltage. Now we're doing it for resistance. Where did we lose you? Okay. So again, look at it piece by piece, component by component. So we're treating points A and B as their own little entities, because that's where we're going to measure across to get our resistance. So you just start with one connection. So A, what's A connected to? And R4. Because remember, this is just a piece of wire. So we want to go from one component to another component. So that's why we have point A connected up to one side of R2, one side of R5, one side of R4. We don't hit anything else before we get to those components. So that's what we've laid out here. Then we just have to start figuring out where all the different connections are. So we can start either R2, R5, R4, doesn't really matter. So in this case, I just took R2, and what is R2 physically connected to on the other side? R3 and R4. And how many connections can you make between those? One. There's only one path you can go to get to either one of those. Hence, why this turns into a series connection. So then we have R3, and R3 is connected to point B and the other side of R5. So all these guys are then going to connect in together into one point as well. So this here is R Thevenin. What's the resistance that we're going to be seeing at point A or B? Okay? I have my notes on this guy.
So I guess I'm kind of confused. So if we already know R1's value, then what's the point of trying to find R7?
So the point is we're trying to find the voltage and current of this guy. Because once we have the voltage and the current, then we can solve the rest of the circuit. And that's the end goal, is we're trying to get the voltage dropped across each of these guys. So, put my marker down. We're going to have 12 ohms in parallel with 15 ohms. That's going to be added to 27 ohms. And then that's going to be in parallel with 15. So 12 in parallel with 15 gives us what? Okay. We're good with that? So this value, 6.667 ohms. We're going to add 27 to that. So that gives us 33.667. And then we're going to take that in parallel with our 15. 16. .846 ohms. That's our R Thevenin. Yep. So there's our two values. Our R Thevenin and our V Thevenin. Yes. If the board will cooperate. Okay. So we've removed R1, and now we're just looking at what voltage are we going to have going from point A to point B. So literally, I'm going to walk from A to B. What voltages am I going to encounter to get there? So yeah, so 74 is going to be dropped across this whole branch. So then we got to figure out how it's going to break down. So we got to take this guy, combine those together in series. Now we have a single resistor in parallel with a single resistor. We got to combine those together, and that's where we get our, right here. That's this one is our parallel resistance. So then what we have to do is then we're going to use voltage divider, because now we're down to a simple series circuit. We want to find how much voltage is dropped across this guy. So we take the 12 volts or 12 ohms divided by the R total, which is the 121, which is all these guys in parallel added to the 12. Because all we're doing is we're trying to combine this together to a single R total to work with our Thevenin.
So like R2, R3, and R5 all together?
Yes.
Okay.
Yep, R2 and then R3, R5 in series with R4 in parallel.
Okay.
So then we get the 38.407. So now that we know that we have 38.407 here, and we have the rest being dropped across the entire parallel branch. So we've got 38 here, we've got 35 here. Then what we need to do is we don't care about the voltage drop across R4. It's not being used right now. We don't care about it.
That's the 35.993.
Yes. So 35 is going to be dropped across that whole guy. What we do care about is this portion here. So we have 35 being dropped across this whole section. We need to find out how it's going to split up between those two resistors.
Then can you do the voltage divider, so the 35.593 voltage divider with R3 and R5?
Yep.
Okay.
So that's where we have here. So then we get the 22.349. So then we got to look, okay, we're coming from here and we're coming this direction. We pass a positive 38.407 and then we pass a positive 22.349, which gives us this value. So that's the voltage we would measure if we had this circuit hooked up. Okay, we good there?
Yeah.
So now we throw it into our Thevenized circuit. So we've got 60.756 volts. Our R Thevenin is 10.846 ohms. And our R load, which was 27 ohms. So now, at this point, what we're going to do is we're going to be solving for the actual values of R1 in the main circuit. So now, it's just a simple matter of using voltage divider. So the voltage of R1 is going to be equal to 27 ohms divided by the 37.846, which is just adding these two together, and then multiplying it by our total voltage, which in this case is V Thevenin, 60.756 volts. So looking at that, we should have about 2/3 of the voltage being dropped across this guy. So we should be seeing around 40 volts. So how much? Okay. Sounds about right. Okay. Yep, we're good there. What I will do though is I will carry it out just the 3 decimal places. Okay, so this is the voltage. The last thing we need to find is the current of R1. So we take the voltage of R1, divide it by the resistance. So we get 43.344 volts divided by the 27 ohms. 1.605? Right. I'm used to writing milli because that's a lot of what we deal with is milliamps. So 1.605 amps. Now, oops. So what we're going to do is we're going to take this value, now we're going to put it back into our original circuit. So we got 43.344 volts and 1.605 amps. So we'll come back to our original problem. And we'll put those values in. So now, what we're going to do is now we're going to use Kirchhoff to solve for the rest of these voltages. So the first loop I want to do, I'll start down here in this quarter and I'm going to go up this direction. So I'm going to come through here, come across, go down, back to where I started. So when I do that, we will find the voltage for R5. So VR5 will be solved as follows. So we're going to hit a negative 74 plus a 43.344 plus the VR5 has to equal 0. What? 656. We can plug that number onto our equation now, or into our circuit. Now, the next way I can go is we'll do another loop. Again, I'm going to start in the same place. We're going to come up. We're going to go over here. We're going to go through R1. And then, let's see. We can go through R3 and R4. What am I missing?
Well, we know the voltage of R3, don't we? We saw that at 10.
We do.
8.386 volts.
We do know that one, but we shouldn't have to solve for that one again.
Well, yeah, we've already solved for it.
Right, we're assuming that we didn't, is what I'm saying on this one. So, why did my mind completely go blank on me? I apologize. Only one unknown. And that's what did I goof on?
So what's the current used for then? You could use voltage bar across and run that current.
That's what I was. Oh, that's what we do. We have. That's the step I was skipping. That's why we have our current. So, sorry, a total brain fart. I apologize. So now that we have these values, let's look at our currents. Okay, just like what we did before. We've got 1.605 amps here. How much current do we have down here? Yes. Okay. So we have 1.916 amps coming up through this guy. We've got 1.605 amps going this direction. They're not because of this component here. Yes. So we're going to have current split that direction. So now that we have this, how much current do we have going through R3? Okay, we have 311 milliamps. How much voltage do we have dropping across R3? Which is where we got the 8.397 last night, or yesterday. Okay, so now, like I said, we can have confidence in this because we did already solve for this value yesterday. That was what I was jumping, thinking we were only doing voltage. Now we come back, we do another voltage loop, where we come up, we go over, come through, and go down. So now what we have, we're solving for VR4 because we have one voltage, an unknown, and another voltage. That all has to equal 0. So we take VR4 is equal to the 74 volts minus 43.44 or 344, and we minus the 8.397. And how much voltage does that give us left over? So how much do we get? Okay. And then we have one last loop to run, where we'll come up through here, across, over, and down. 702? 712 volts. It does, like I said, once you get that resistor, everything is just going to start flowing out really easy just by using Kirchhoff's laws. So, in recap, once we found this voltage across R1 using Thevenin's theorem, we found the voltage and the current. We can then plug it back into the original circuit and start looking at loops. When we make a loop, we want to do it so we end up with one voltage value that we're missing. So we come up, we come down through R1, or go through the source, come down through R1, come through R5. R5 is the only one we don't know. So we have our 74 source. We're dropping 43, which means we have to drop the 30.656 here. Then we find the current of R5, because that's the next bit of information that we know. We find how much current we have here, find out how much current we have here. We use Kirchhoff's current law at this node to find how much current we have going out or going in, is whatever the case may be. So then what we'll see here is we have this much current. We take this current and this resistance is going to give us a voltage. Now we can run an additional loop through one of the values that we know into either one of the other ones. We could have just as easy run over down through R2, through R3, through R5, and we would have gotten that 51 volts. Then it's just a simple matter of one final loop of being dropped across those two resistors. Now, if we wanted to double check to make sure that we had this work. Kirchhoff's voltage law states in any loop should equal 0. So we could even double check it. I know there's a lot of writing on here, I apologize. If we were to do a loop in that square. Okay? If we started here, we're going to have, so negative to positive based on the current. We're going to have a negative 8.397 volts. We're going to have a positive 32. That's not right. Did we? Yeah, we flipped that. I flipped that. So we're going to come around. We'll have our 8.397. We'll have our positive 22. And we'll have our negative 30.656. And that should all come out to equal 0 or close to. So coming through this guy, we had the 74, the 43, just the way the current flows. I flipped my current in the middle of it. Yeah. So like I said, I wrote it down incorrectly. So then, like I said, we double check. We can just do a quick double check and make sure any of these loops equal 0, which we know this one does, and we know this outside one does. So if we have those two loops, we're pretty confident that that middle one's going to add up. Okay. Like I said, there's a lot going on. There's a lot that we're doing, but once we find the Thevenized or once we use Thevenin to find the voltage across this guy, the rest of the circuit becomes easy compared to what we have been doing. It's just tracking how much voltage is going places and how much current is going places. Okay. So my plan is we're going to go through another one of these, but first, we need you guys a second to kind of digest this a little bit. I'm not going to completely overwhelm your brains. We're going to jump back and do another style of Thevenin based on the quizzes, and then we'll come back and do another bridge.
What was the first quiz?
Huh?
Is it the first quiz?
The unknown, yes.
I took it like 5 times before I did it.
All right. So we're going to start off again simple, where we have a resistor, and then that one is in parallel. So R1, R2, and R3. What we're looking for are current total, VR1, VR2, and R3's value. So we're going to start with 84 volts. R1 is 18 kiloohms. R2 is 27 kiloohms. And our current across R3 is 1.881 milliamps. Now, do we have enough information to solve this equation as it stands? Yes. Given to us. Yep. Yes. So the answer is yes, we do have enough information. We just have to look at it differently. With how the circuit is drawn, though, like this, do we have enough information to do anything with it? Just this circuit alone? No, because we don't have voltages, We don't have currents. Like this one, we're missing 2. This one, we're missing 2. We don't have enough. So this is one of the aspects where Thevenin comes in handy. Because wouldn't this circuit be a lot easier if we could just remove or get rid of one of these components? R3, for example. So if we take this out, we're going to Thevenize R3. So just like what Carson was saying, we're going to now do this. We've removed the load. Now we need to find the voltage drop across A to B, which is our Thevenin voltage, and the resistance from A to B. So V Thevenin is simply what at this point? The voltage drop we would have across R2. So we have 27K and an 18K. They're in series. So we're going to use voltage divider. So we have 27K over 27K plus 18K. Multiply that by 84. What's our V Thevenin? Okay. Our R Thevenin, we're going to short the supply and calculate the resistance based on this. So what is the formula to solve for the resistance of AB? Correct. So R Thevenin is equal to R1 in parallel with R2. And Fallon, what does that give us? Okay. That's R Thevenin. Yep. Yep. Okay, then what's our... All right. 2 resistors, product over sum is just faster for me to type it in my calculator. All right, so we have these 2 values. Well, where do we go? Let's take it to the next step of Thevenizing. So we take our Thevenin circuit, we plug in what we have, and look. So we have 50.4 volts. We've got 10.8K. We're back down here to R3, which we don't know its value, which is what we're trying to solve for. But we do have the current. So the current through here, I Thevenin, is 1.881 milliamps. Because that's the whole point of Thevenizing something, is it's to give us the voltage and current of that component. So, if we have 1.881 milliamps going through R3, what do we have going through R1? The same thing, because they are in series. Or sorry, not R1, R Thevenin. So now, what do we have? What can we solve for? Yeah, Ohm's law. What can we solve for? We can solve for the total resistance. We can solve for the voltage drop across this guy. We got so many different paths. One of the things I like to do is solve for the resistance. Save one extra step. Okay? So the resistance total of this circuit, let's do that resistance total in Thevenin, is the voltage total divided by the current total. So we have 50.4 volts divided by 1.881 milliamps. What does that give us? So we have 26.8 kiloohms. If we have So obviously when we're solving these, we want to keep it out 3 decimal points, so that'll probably change a couple of these values just a little bit. But just rounding it off right now, just for simplicity's sake, we've got 26.8K of total resistance. If we have 10.8K of resistance already in this circuit, how much do we have to have across R3? 16. So we end up with 16 kiloohms. Like I said, based on rounding, it's going to be slightly above or slightly below what we're actually calculating. This is just a rough estimate off this. Should still get you fairly close. I think with these values, you should still be within the 5%. Okay? So, now we can come back and look. So we were able to find our R3 value using Thevenin, and we just kind of worked it backwards. So now we come back to our original circuit. We plop this guy back in, and we know 2 things. We have 16K ohms here, but what also can we determine? The voltage drop, which we could have also gone this direction as well. We could have gone through and found the voltage across this guy, subtracted it from our total in Thevenin, and that would have given us the leftover here, which then we wouldn't have to calculate again because we'd have that value. But like I said, we can go about it either way, solving for total resistance, solving for total voltage, and subtracting out that way. So we end up with how much voltage across R3? How much? Okay. That's using the full numbers without rounding them off. Okay. Using numbers with that we got here with rounded off, I had 30.096. So 400 millivolts. 685. These 6s are easy to turn into 8s. Okay? So now that we have that, what is the voltage that we're asked in our original question? What's the voltage of R2? 29.665. 685, however you rounded it off in your calculator. So if this voltage is 29.685, what's the voltage of R1? 315. Okay. So now we've got our VR1 and our VR2. And we have the resistance value. So the last step we need to solve for is the current. Again, we could do this one of 2 ways. Where is our total current in this circuit? R1. Because it's directly in series with the source. So the current of R1 is our I total. We have the voltage, we have the resistance, we can solve for it. So I total is equal to IR1 What'd you say?
3.012 million.
That's it. So here's our final answer. Here's our final answer. And here is our final answer. And this guy.
Yeah, it's definitely not that.
Do what?
That's just like a lot of steps.
There is a lot of steps.
I'm just like trying to like keep it organized and like brain, like keeping it like square on paper. So I'll just get lost in the sauce of just like everything written down.
Right. I like that expression. Okay. We'll go through another one of these. And I will try and spread it out a little bit more so we can see it. The hard part is I'm trying to keep it all on one screen. So I jump back and forth, and I don't want, I don't want to be having to scrolling back and up and forth to get numbers. So that's part of my fault. This is true. Or what I need to do is learn osmosis and split myself in half, and then form back together. That could be fun too. So that's somebody's final project.
I watched that movie and I felt like that's about it.
That's your guys' final project.
I watched that movie and I feel like this is a bad idea.
Obviously, I don't want it to be permanently fused into my skull or into my spine. I want it just like a suit that I can put on, and maybe a neural connection. I'm okay with that. Do what? Okay, let's do another one. I'll try and spread it out again, and I'll compensate for that. So, all right. Then, like I said, we'll jump back in and we'll do another one, another of the bridge circuits. Do what? All right. That's true. That's what I should do. It can be. Do what? It might.
I think they're vectorized.
Oh, okay. I thought you meant like the opposite one.
I can make it smaller. Let's try that. We'll see how bad my handwriting is. Okay, so we got 8 volts. R1 is 39 kiloohms. R2 is 82 kiloohms. And IR3, 82.86 microamps. Yep, we're solving for the same thing. We want I total, VR1, VR2, and of course we need to know what R3 is. So, first steps, we need to pull out R3 so we can Thevenize to that location. Second step, we're going to solve for the V Thevenin. So V Thevenin is equal to the voltage from A to B, which in this case, it is VR1 as it's drawn after the removal of R3. So the big thing to remember is once we start to Thevenize, we're changing the circuit. So the values we're finding here are not the actual R1, R2, whatever values. It's just for our Thevenin analysis. So if you have to, when you're making your notes or when you're writing down your answers, block off a section and say, Thevenin only. Because anything that we label in this section is not going to be our actual answers until we get out of doing Thevenin. So, in this case, VR2 is going to be, we're going to use voltage divider. So we have 8 volts, and we multiply that by our 82K divided by the 82K plus 39K. Because all we have in this instance is just a simple series circuit with 2 resistors. Just voltage divider. When we come up with that, we get 82 divided by 82 plus 39. We get 5.422 volts. That's V Thevenin. So then we need to solve for our R Thevenin value. So R Thevenin is the value we're going to get if we were to put a meter between A and B and measure it. And first, we short out the load. And the reason we do that is this voltage source, in theory, is supposed to have 0 ohms of resistance. It's not supposed to contribute anything to the resistance. It just spits out this amount of voltage, which we know doesn't happen. It has some. We've seen it when we measure resistance and we have it plugged in. It's going to change those values. But theoretically, it should work with 0 ohms of resistance. So this is why we have to short it. So when we look, to get to point A to point B, what do we have? We come across A, and what's A connected to? R2 and R1. And then what's the other sides of R2 and R1 connected to? B and each other. So with that, that's all that we have. So if R1 and R2 are connected on opposite sides together, we have those guys in parallel. So the R Thevenin is going to be equal to R1 in parallel with R2. So when we solve this, we're going to get a value that's going to be around 30K ohms. It's going to be less than the 30, but as this gets farther and farther away from it, we're going to start approaching our smallest value. That's why, like when we use our voltmeter, it has 10 megs of resistance. If we put it in parallel with a 1K, we still have about 1K. So we get 82 in parallel with 39. What'd you put it as? Oh, yes. That would change your answer, but that makes sense. That's what I was thinking. I was thinking you were off a factor. So what'd you get? 26.43. Okay. We good there? Now, we're we're going to take that and plug this into our Thevenized circuit. So we have 26.43 k ohms. We have 5.422 volts. And we can look back at our original equation because these two are identical. We have 82.86 microamps here, which means we also have that value across here. Now what I want to do is we need to solve for this resistance value based on these parameters. What I'm going to do is I'm going to solve this in terms of voltage because we need this voltage across this guy anyway. So we might as well solve for it and go that direction instead of having to do an extra calculation at the end. So if I have 82.86 microamps, I'm going to have that same current flowing through my entire circuit. So I have 26.43K I'm going to multiply that by 82.86 microamps. And how much voltage does that give me across this Thevenin resistor? So VR Thevenin is equal to 26.43 kiloohms multiplied by the 82.86 microamps. And what's that? 2.19 volts. So which means I'm going to subtract the 2.19 from my total voltage here. So 5.422 subtracted by the 2.19, that gives me 3.232 volts. Now that I have my current, I have my voltage, I can solve for the actual value of R3. So R3 is equal to the voltage of R3 divided by the current of R3. So we get 3.232 volts divided by the 82.86 microamps. What does that give me for a resistance? R3. 39K. To be precise, 39.0056, whatever. Like I said, it's not gonna just so like when we're calculating these, that's where we're at. We're knocking off 6 ohms when we're compared to 39,000. I don't really care about those 6 ohms. It's not gonna. Our meters are gonna fluctuate that much. Okay, so that comes out and that gives us this value. Now what we need to do. So now we can move out of Thevenin because we've used it to its full extent. We step out, we come back to our original circuit, and we know that based on the Thevenin analysis that we did, we have 39 kiloohms with a voltage of 3.232 volts. Now, since these guys are in parallel, our voltage for R2, the real R2, is this guy right here. because they're in parallel. Then we solve the voltage across R1 because these guys are going to have the same voltage drop across here. Whatever's left have to be dropped across R1. So the voltage drop of R1 is equal to our 8 volts minus 3.232 . And what does that give us? 4.768 volts. And then the last step we need to find, so we've got this guy, and this guy now, is our I total. I total we could find by total voltage, total resistance, or the current going through R1, because that's going to be the same. Yep, because it's in series with the source. So I total is going to be equal to the current going through R1, which is voltage of R1 divided by R1. And we get 4.768 volts divided by 39 kiloohms, giving us a grand total of 122 microamps. Then, just as a double check to make sure these numbers come out believable at least, we have 122.256 microamps at R1. This current is going to split between R2 and R3, and we see that we're only drawing 82 over here. So that works out. We want to make sure that we have enough current supplying this that we're at least have the 82.8. If we got a smaller number than that, we did something wrong with our calculations. So somewhere along there we could have dropped it in like Zach did in the 3,900 instead of 39,000. That's where we could double check our answer because it's going to be way off from what would be needed. If we fat fingered it, we could have 12 microamps going into the circuit where we need 86 to meet these conditions. All right. We'll go ahead and go to break. When we come back, we'll do another bridge circuit. Do what?
We're doing a lot of twisting, but I can feel it.
So Seth, this will be fun. The next section we're going to do universal shunt meter has 3 1/4 pages of notes. 3 1/4 pages of notes for the next thing we're doing.
Oh, let's have Gander. Dude, lunch was wild today. My homie, he dared me to take some prescription schizophrenia pills. Just dared me. And they started disappearing.
That's funny.
That's my favorite pill. So shunt meter. I'd ask you what it is, but you're going to tell me anyway, so. I'd ask you what it is, but you're going to tell me anyway.
It's a current meter that has built-in protection when you're shifting ranges.
So that's not the take out, put another range, take out, put another range. This is click.
This is the click, but as you're in between clicking like you're doing with the range, if you went from 17 down, your meter's going to peg. When you do it this way, it won't. There will always be resistance.
Oh, that's cool. So is it kind of a combination between the voltage meter and the current meter that's
Yep.
built?
It's a current meter, but it's built to protect itself.
Oh, that's sweet. That's sweet, man. Fun stuff to learn.
See, this is the problem is this is stuff I actually really enjoy. And other than that brain fart I had, I enjoy teaching it, and that's why I start getting faster and faster because I enjoy it.
Oh, buddy. Everybody has brain farts. Come on.
I know. Hey, I'm allowed to have one. So I've only had, I think this is my second brain fart this semester.
Teachers are allowed to have at least 6 a day.
Well, it's better. It's my first semester. I was having, oh, jeez.